Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. Today, the term JDM is widely used to describe Japanese domestic market vehicles produced throughout the 1980s and 90s. The Toyota Supra and AE86, the Nissan Skyline GT-R and Silvia, the Honda Civic and S2000, the Mazda RX-7 and MX-5, the Subaru Impreza, and the Mitsubishi Lancer Evolution. While globally popular, these vehicles are aging, and failures are inevitable. In fact, vehicles from this era, not just JDM models, may be the last generation that is truly DIY-friendly. To tackle DIY repairs, you first need to understand how their systems work. In this video, we're going to dive deep into how JDM ignition systems actually work. The mid-1980s marked a major technological transition in ignition systems. Consequently, early and late JDM vehicles utilize fundamentally different ignition system designs. First, however, we will review the basic principles of spark ignition. This diagram shows the basic configuration of an ignition system, consisting of a battery, a switch, an ignition coil, and a spark plug. Inside the ignition coil, two windings, the primary winding and the secondary winding, are wound around an iron core. As long as the ignition switch is on, the primary winding is constantly supplied with 12 volts from the battery. When the switch in the primary circuit opens, the current flowing through the primary winding is interrupted. At that instant, a high voltage of 300 to 500 volts is generated across the primary winding. This creates an even higher voltage of 10,000 to 30,000 volts in the secondary winding, which then fires the spark plug. In vehicles manufactured up until the 1970s, the primary current was switched either by contact breaker points operated by a mechanical cam, or by an ignition system that replaced those points with a transistor. However, since these systems predate the JDM era, they fall outside the scope of this video. In 1980s JDM vehicles, an electronic ignition system paired with a distributor is primarily used. The system consists of a spark plug, an ignition coil, an igniter, and a control unit. When the ignition signal from the control unit is off, the transistor inside the igniter remains off, and no current flows through the primary winding of the ignition coil. As the ignition timing approaches, the control unit sends an ignition signal to turn the transistor on. This allows current to flow through the primary winding, preparing for ignition. Once the optimal ignition timing, calculated based on signals from various sensors such as engine speed and throttle position, is reached, the control unit stops the signal. The transistor then switches off, interrupting the primary current and causing the spark plug to fire. In this system, the distributor distributes the high voltage to the spark plug of each cylinder. The terminals for each spark plug wire are arranged around the circumference in the engine's firing order, while the center terminal is connected to the ignition coil. A rotor driven by the camshaft receives the high voltage at the center terminal and distributes it to each cylinder in sequence. For example, on the AE86 Generation 4A GE engine, the distributor is mounted on the side of the cylinder head, adjacent to cylinder number 1, while the ignition coil and igniter are mounted together near the strut tower. On the EF, EG, and EK Generation Civic's B16A engine, the distributor is mounted at the rear of the cylinder head and integrates both the ignition coil and igniter. In the mid-1980s, two major transformations occurred in ignition systems. The first was the wastedspark ignition system. Using two ignition coils, it fires the spark plugs of the number 1 and number 4 cylinders and the number 2 and number 3 cylinders simultaneously. When the number 1 cylinder is at top dead center on the compression stroke, its spark plug fires to begin the combustion of the air-fuel mixture. At the exact same time, the spark plug for the number 4 cylinder also fires. However, the firing of the number 4 plug serves no purpose, and this is referred to as a wasted spark. This system offers two major advantages. Since a distributor is no longer required, electrical losses inside the distributor are eliminated. In addition, using two ignition coils provides more time to charge the primary coil, which prevents the spark from weakening due to insufficient electrical power, particularly at high engine speeds. In Toyota, this system was featured in the AE101 generation Corolla with the supercharged 4A GZE, as well as the A80 generation Supra, equipped with the 2JZ GTE. Other examples include Mazda's B6 and BP engines in the MX-5, and Mitsubishi's 4G63 in the Lancer Evolution. The second major change is the direct ignition system, which is also commonly referred to as a coil-on-plug system. In this system, an individual ignition coil is allocated to each cylinder. As a result, not only the distributor but also the spark plug wires became completely unnecessary. Furthermore, it can maintain spark intensity at high engine speeds, better than the wasted spark system. As will be explained in detail later, the primary benefit of this system is the ability to adjust ignition timing individually for each cylinder. While most modern engines adopt this system today, the world's first were the RB20DET and RB20DE engines featured in the R31 generation Nissan Skyline. It is highly interesting to note that, while the first generation of Toyota's 1JZ and 2JZ engines featured a high-performance direct ignition system, the second generation was downgraded to a wasted spark ignition system. Although this decision remains puzzling, the true reasoning is known only to insiders within Toyota. And today, those who understand the background behind it may have already retired. On the other hand, the fact that aftermarket coil-on-plug conversion kits to upgrade these engines are highly popular in today's JDM scene, 3 decades later, is perhaps part of its enduring appeal. To precisely control ignition timing, it is necessary to accurately detect the engine speed and piston positions. The detection methods used in early JDM engines are classified into several types, based on the sensor variants and mounting locations. One of them uses sensors installed inside the distributor or at the end of the camshaft, for crank angle detection and cylinder identification. An optical sensor detects the rotation angle by using a photodiode to sense light interrupted by a slotted rotor. For example, the rotor in Nissan's RB20DET features 360 slots for detecting the cam angle and 6 holes for cylinder identification. The pickup coil sensor senses the rotation of a signal rotor with gear-like teeth using a coil. In the Honda B16A engine, a signal rotor and pickup coil assembly inside the distributor detects engine speed and identifies the cylinder. These camshaft-based detection methods have a weakness, where the detection signal becomes inaccurate at high engine speeds, due to the flapping of the timing chain or belt. Engines such as Toyota's late model 1JZ and 2JZ, as well as Subaru's EJ20, feature a signal rotor and a pickup coil sensor installed directly on the crankshaft. The crank angle is detected using a crankshaft rotor with 36 teeth minus 2 missing teeth, while cylinder identification is handled by a 3 or 4 tooth camshaft rotor, depending on the number of cylinders. In the 2000s, as highly precise Hall effect sensors became available, the method of directly detecting crankshaft rotation became mainstream. The Hall effect is a phenomenon where bringing a magnet close to the current flowing through a Hall element changes the element's voltage. For example, in the Honda Civic, the B16A used up to the EK generation featured a pickup coil sensor inside the distributor, whereas the K20A in post-EK generations utilizes a Hall effect crank angle sensor. Knocking is a phenomenon where abnormal combustion occurs at a secondary location within the combustion chamber after spark plug ignition. The ignition sources include overheated exhaust valves and accumulated carbon deposits. When knocking occurs, the pressure inside the combustion chamber rises abnormally, causing fatal damage to the engine in the worst case, such as melting a hole in the piston. To prevent this, knock sensors have been installed in engines since the late 1970s. Since knocking transmits specific vibrations to the cylinder, a piezoelectric element inside the knock sensor captures these vibrations to detect the knocking. Generally, one knock sensor is installed on the side of the cylinder block for 4-cylinder engines, and 2 for 6-cylinder engines. When knocking is detected, the control unit retards the ignition timing until the knocking signal from the sensor disappears. In systems prior to direct ignition, when knocking was detected in one cylinder, the ignition timing was retarded for all cylinders. The Nissan RB20DET engine, which features a direct ignition system, uses cylinder-by-cylinder control to retard the ignition timing only for the cylinder where knocking occurred. This is possible because it has an individual ignition coil for each cylinder, and can detect the crankshaft angle every 2 degrees, using a precise cam angle sensor with 360 slots. On the other hand, how is it for Toyota's 1JZ? As mentioned previously, the early model 1JZ uses direct ignition, while the late model uses wasted spark ignition. Optimistically assuming Toyota's capability, one might expect cylinder-by-cylinder control for the early model, and 2-cylinder group control for the late model. However, the 1JZ control unit only determined the crankshaft angle every 30 degrees for the early model, and every 10 degrees for the late model. In modern engines, even if the crank signal is every 10 degrees, the control unit interpolates between them to estimate the precise crankshaft angle. But computing power back then was only at this level. While our curiosity is endless, we could not find detailed technical documents. So, let us leave that as a mystery. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.